Hi, I'm Hayden Shanathan. I'm technical staff in the Lincoln Laboratory Supercomputing Center, working underneath Dr. Jeremy Kepner. Our demo today is focused on GreyNoise enriched analysis of CAIDA network data. This demo is an example of a Jupyter notebook, which is a common tool used by researchers both for prototyping code and for sharing code amongst each other. Our plan is to start by talking about the two data sets we're going to be cross-correlating, and then using that cross-correlation in order to look at large-scale behavior of our network traffic data. We're then going to look a little bit closer at individual variables and their statistical distributions. And then finally, we're going to look a little bit at some AI ML algorithms that we're investigating for clustering IP variable pairs. The first thing, of course, we need to do is load any necessary packages. This includes our Python D4M library, some custom utilities specific to this analysis, some standard dense and sparse linear algebra libraries for Python, some graphing utilities, a Python general purpose serializer, both for loading and storing our data, and some standard Python libraries. Now, our first data set, of course, is taken from GreyNoise, which is an internet-wide sensor network which both analyzes and tags their collected data. We can then cross-correlate this with another data set, for example, a data set given by you. In our case, we're going to be looking at the CAIDA data coming from their network telescope. Now, the CAIDA network telescope is a globally routed /8 network carrying negligible legitimate traffic. And this makes it a natural observation point for looking at anomalous, unsolicited traffic. Specifically, we're going to be looking at 30-minute windows that were collected on 4 different dates, 2 of which were at midnight and 2 of which were at noon. So here we can see a snippet of some of the information from the cross-correlated data. Each row corresponds to a source IP, and each column corresponds to values associated with them coming both from our GreyNoise tags and from our CAIDA data. So for example, this first source IP, which I should stress are all anonymized, has an unknown actor, and this is largely the case for all of our data, as we'll see. It has an ASN associated with it, or autonomous system number. It's either classified as malicious, unknown, or benign by GreyNoise. In some of the cases where it's classified as malicious, GreyNoise also has a CV, or common vulnerability, or an exploit that was utilized, or at least attempted to be utilized by that source IP. We also have the last seen timestamp as seen by GreyNoise, the operating system associated with that traffic, any protocol ports used by that source IP, whether or not it was possibly spoofable, and finally, the number of source packets that were sent by that source IP address during communication with CAIDA during its 30-minute periods. Now, these are all anonymized. These anonymized TSV files are then processed into D4M associative arrays and then stored according to date. So, for example, our first associative array here corresponds to the entire table that this is a snippet of, while the next few associative arrays correspond to the individual variables for these columns. These last 2 associative arrays for each date correspond to data that appeared inside of CAIDA, but did not appear within GreyNoise. So we're going to go ahead and deserialize each of those different arrays, which we can see happens very quickly. And we can then use these associative arrays that we've unpickled or deserialized in order to create an exemplar record. In other words, we're going to go through each of our different variables, figure out what the most common values associated with those variables are and how often they appeared. And so here we've looked at, for a specific date, here our June 17th date, we looked at the maximum count and maximum value associated with actor, ASN, classification, CVE, OS, and protocol port. So for example, as mentioned before, our actor in 99.63% of cases is unknown. So the vast majority of the time, we don't know what actor is utilizing that source IP address. The ASN is a bit more varied. Here we have about 5% use this ASN 4134. Classification, we see that the majority, about 60%, happens to be classified as malicious by GreyNoise. And in fact, if we looked a little bit further at it, we'd see that those that aren't classified as malicious are very, very often classified as unknown. Very, very few traffic is classified as benign, which is to be expected since this is all illegitimate traffic. Now, perhaps the most interesting row in here is that corresponding to the CVE. We see that 90% of the time, that CVE happens to be CVE 2017-0144. So in particular, a single exploit is being used 90% of the time. This exploit is commonly known as Eternal Blue. The OS, most common one for about 36% of the time, is Windows 7/8. And then the most common protocol port that we see about 22% of the time is TCP 445, which corresponds to Microsoft networking. So in other words, we can take our GreyNoise data and cross-correlate it with a given data set for network data and use that in order to summarize the behavior of billions of packets and find what the major features of that network data happens to be. Next, we're going to look a little bit closer at some particular variables and look at their statistical distributions. So for example, let's go ahead and look at the distribution of ASNs for malicious records in particular. And we see that it's fairly variable for each individual date and spikes quite a bit different areas. If we were to actually look up what each of these ASNs actually corresponded to, we'd see that they kind of run the gamut of telecommunications entities, including ISPs, wireless carriers, and so on. And the countries that end up being represented the most often include Vietnam, China, Taiwan, including also Russia and Turkey. So here we look specifically at records that have been classified as malicious. We can, in fact, we have a lot of flexibility here for what additional criteria we add to our selection. So it's very robust. We can add as many criteria as we want. For example, if we wanted to just look at the ASNs of malicious records, which utilized a particular CVE, we'd be able to do that. Maybe we only want to look at those that actually are using Windows 7 or maybe Linux, etc. Next, we're going to be looking at how things vary over time. So we're going to be looking at malicious data, how that last seen timestamp differs over time according just to the hour of day over a 24-hour period. So we see that for those collection periods at midnight, we see that they're very closely associated with one another. And same thing if we look at the collection periods of noon. Now, previous work that we've done with network data before has shown that heavy-tailed statistical distributions are very, very common and emerge very often. In particular, a very commonly seen one follows the Zipf-Mandelbrot model, which we can verify actually occurs in our cases as well. So here we have the distribution of packets sent from malicious sources. We can see in particular that over each day, or for each of our 4 different data collection dates, they're all very, very closely associated with each other. And so in particular, our model very closely fits all 4 of the collection dates. Here, this model is known as the Zipf-Mandelbrot model, and we can figure out using some gradient descent methods what the parameters for that model happen to be. We've actually seen that this holds even more generally the emergence of this Zipf-Mandelbrot model. So if we were to look at the distribution of the frequencies of ASNs, we see that this follows very, very closely a linear on a log-log scale, which is a heavy tail distribution, or in other words, the distribution's tail peters out very, very slowly. And here we can also calculate the Zipf-Mandelbrot model parameters and see that this holds much more generally. So in other words, we can examine the distribution of value frequency using a robust selection criteria. And then we see as well that some heavy-tailed statistical distributions verify the time-independent statistical phenomena and illustrate the general applicability of the Zipf-Mandelbrot models, which we can calculate the parameters for. We're going to end off by briefly looking at some of the AI ML algorithms that we're using to cluster IP variable pairs. In particular, we're going to be looking at topic modeling via sparse non-negative matrix factorization. So we're going to go ahead and set the associative array that we're actually going to perform this topic modeling on, along with setting our hyperparameters and initial values. We're then going to run the model, which takes a few different iterations, usually only takes about less than 20. See, we've already reached our N, and we can see what that model actually produces. So the non-negative matrix factorization, it gives a approximation of our original array, which is the product of two smaller associative arrays. And here we actually have the plot of what those associative arrays look like. So utilizing some AI/ML techniques like sparse non-negative matrix factorization is allowing us to create some new analytic tools for analyzing data and better understanding how IP and variable pairs interact with one another. So that's the end of my demo. Thanks.